So it's time for a test. And so the next few videos are going to go over material for the test. But really, yeah, I mean, the test covers all the math you've been learning in the last couple of years. so so I don't know how you prepare for something like that, except that you've been preparing for it over the summer with the summer packet and in the last few weeks by engaging with all these review of concept videos and assignments we've been talking about. But I thought we could look at some things that either were troubling for people along the way or are traditionally troubling for people. This is not to indicate that any of these topics are more represented on the chapter test, but I think they're all reasonable test questions. And I'd look first at this one. What's the difference between this versus this? Okay? Why don't you think about that? See what you can write for that. Uh, think about what each of those is asking and why even think there's a difference between them. But there is. Yeah, so think about that. Pause the video and think about this for a minute. Well, welcome back. Um, so when I think about sine x equal negative 1/2, I think, wow, that happens an infinite number of times. It happens here at 7 pi over 6. It happens here at 11 pi over 6. And so the answer to this might be 7 pi over 6 plus 2 pi n, 11 pi over 6 plus 2 pi n, because there are an infinite number of solutions. You know, if I had been given some sort of domain restriction, then I would just lead with these answers. But when I think about this, what angle within the restriction has an upness of negative 1/2? Well, it's neither of these. Remember, there is a restriction on inverse sine that we go from negative pi over 2 to pi over 2. And these aren't within that restriction. Pi over 2 is here, negative pi over 2 is here. And so that's the answer we're looking for. And that answer is negative pi over 6. Okay? Why don't we practice one more of those um, and see if you feel a little more comfortable with it. How about cosine inverse root 3 over 2 versus cosine x equals root 3 over 2? Try that one. Right, so we know this one has only one solution, and that solution is pi over 6. But this has an infinite number of solutions. When we think about the cosine graph, and we think about positive root 3 over 2, there's an infinite number of points of intersection. Remember, though, that the restriction for cosine is between 0 and pi. And we only get that one solution there between 0 and pi. That's why this one only has one solution. But there are many solutions. There are an infinite number of solutions. So we could say pi over 6 plus 2 pi n. And where's this one? Well, the overness is positive root 3 over 2. Cosine is positive in quadrants 1 and 4. And so this must be 11 pi over 6 plus 2 pi n here. Okay? All right. The next thing that people really seem to find mind-blowing in the last few weeks was this idea of drawing a graph from given information. So, for example, f is decreasing on negative infinity to negative 5, union 2 to infinity. F is increasing on negative 5 to 2. We also know that f is concave down on negative 1 to 4, And f is concave up from negative infinity to negative 1, union 4 to infinity. I have also the knowledge that as x heads to infinity, f of x heads to negative 4, and I know that f of 2 equals 3. All right, so that's a lot of information, and we'll learn calculusy ways of finding all this information, or much of this information, by the time we get to chapter 5. But right now, I just want you to pull all this information together and turn it into a graph. And when we went through this originally, I suggested making a graphic organizer wherein you talked about increasing or decreasing and concave down versus concave up at these various points along the domain of f of x. So I've got this negative 5 as a critical value, and then I have negative 1, and then I have positive 2, and I see positive 4. Okay, so what do we know? Well, we know that f is increasing here and here, and decreasing here 2 to 0, or 2 to infinity? 2 to infinity. Okay, and so I'm decreasing and decreasing. Okay, I also know about concavity. I know that this function is concave down here and here, and I know the function is concave up here, here, and from 4 to infinity. Now remember, when we're talking about decreasing and concave up, that's a specific shape. Decreasing and concave up looks like this. Increasing and concave up looks like this. Increasing and concave down looks like this. Decreasing and concave down looks like this. Decreasing and concave up again looks like that. So essentially what I'm trying to do is stitch together all these pieces in a graph, all right? I notice here at the bottom, I'm also told that as x heads to infinity, the function approaches negative 4. And so this is a horizontal asymptote as we head this way. I don't see anything over here telling me what to do, but I definitely have, as I head in this direction, I should be approaching this y value. And that makes sense to me here. I'm decreasing and concave up as I approach the y value of negative 4. And then this is just an anchor point on the graph. You know, we've got this x value, but by the way, the y value there should be 3. Okay? So let's see if we can pull this information together into a graph. So we've got negative 5, negative 1, 2, and 4. And over here, we need the y value, negative 4. Okay, so I know that 2, 3 is a point on my graph. So I'm going to put that in as a reminder. And then from 2 to 4, I should be concave down and decreasing. So I'm concave down and decreasing until I get to 4. Okay. After 4, I'm concave up and decreasing. Before 2, from negative 1 to 2, I'm increasing and concave down. From negative 1 to 2, I'm increasing and concave down. All right, what about from negative 5 to negative 1? It seems as though I'm increasing and concave up. Increasing and concave up. And then from negative infinity to negative 5, I'm decreasing and concave up. So like that. Okay? Now, the only points I know for sure on the graph, or y values I know on the graph, are this one, and I have to be approaching negative 4 here. This could come much lower, this could be higher. I do have to, though, have where I go from decreasing to increasing. As we go from decreasing to increasing, that's an indication of a minimum on the graph. And when I go from increasing to decreasing, that's an indication of a maximum here. And then remember, we can also glean some information about inflection points. When we go from concave up to concave down, that's an inflection point. And we go from concave down to concave up, that's an inflection point. So there's an inflection point here and another one here, and those are places where we change concavity. We're concave up until we get to that point. We're concave down after that point. We're concave down until we get to that point, and then we're concave up after that point. So where we change concavity is a point of inflection or inflection point. And that can be abbreviated, by the way, IP for inflection point. That's a standard abbreviation. Some people do POI, but I don't because it's extra symbols. So you can use that if you'd like to describe what kind of a point these are. We'll be talking a lot about justifying the existence of inflection points and maxes and mins in Chapter 5. All right, so next, what did I want to look at? Oh, I want to look at some graphing. Y equals, please graph. You shouldn't need your notes for this. You should be able to do each of these, log base 2, if you're ready for a test. Okay? So pause the video, graph this, come back, and check your answers. Okay, so I know that the reference points that I'm supposed to start with are 1 over b, negative 1, 1, 0. b, our base, is 2, 1. And don't forget, because it's a log, it's got x equals 0 of vertical asymptote. And now we need to carry out some transformations. I see one x transformation that I apply to all the x's, including that one. And I see a y transformation here that causes the graph to shift up 1. Okay, so the points that I need to graph are 3.5, 0, 4, 1, and 5, 2. Don't forget that vertical asymptote at x equals 3. Okay, so vertical asymptote at x equals 3. Remember, you need to label it on your graph. 3.5, 0, 4, 1, and 5, 2. Okay. Yeah, those are the points. Okay, and don't forget to draw in the characteristic shape. All right, so there's the first one. Let's do a couple more of these. Remember to send questions when you have them. Y equals 3 square root 2x plus 1 plus 4. Please graph this function. Pause the video, please graph this, come back and check. Okay, so again, I'm going to start off with the reference points, but the reference points for square root of x, are these. And I need to apply these two x transformations and these two y transformations in the proper order to these three reference points. On the outside, I know I'm supposed to follow PEMDAS, so I have to take care of multiplying first. In fact, I'm going to do that in a different color. So multiply by 3, multiply by 3, multiply by 3. And what do I do on the inside? On the inside, I follow SADMEP, so I have to get rid of this before I get rid of this. So I'm going to subtract 1. My transition points are negative 1, 0, 0, 3, and 3, 6. But I still have two more transformations to do. I see multiplying by 2, which means I need to divide the x's by 2. And I see over here, outside the function, that I'm adding 4 to all the y's. This shifts the graph up 4 places. So, where are we located? What am I graphing? negative 1 half 4, 0, 7, 3 halves 10. And remember, this graph doesn't have a domain of all real numbers. This is an endpoint. This is where the graph starts. At negative 1 half 4, this point would be 0, 7, and over here I'd have 3 halves 10. Okay? And if you want to draw in that y-axis and that x-axis, that's fine with me. But I don't particularly need them. I need the points labeled and the correct shape, and I need to see your transformation work. Some students like to do this in their head. Yeah, no, don't do it in your head. I need to see the work, okay? If you don't show me the work, I can't give you the credit. All right, next one. Y equals 2 times 3 to the 4x minus 1 plus 5. Pause the video and graph that one. Okay, welcome back. Now, what were the reference points we were supposed to use for exponentials? Negative 1, 1 over b, 0, 1, 1, b. Our base is 3. And don't forget, exponentials have a horizontal asymptote normally at y equals 0. So any y transformations need to be applied to that as well. So what transformations do we see? Well, this is outside the function. This is inside the function. So SADMEP in here, I have to add 1 to all the x's. This is a y now, so I'm not adding 1 over there. And according to PEMDAS, I'm supposed to multiply the y's first by 2. This is a y, so I'm multiplying it by 2. So my transition points will be 0, 2/3, 1, 2, 2, 6, and 0 times 2 is y, still y equals 0. Okay, what's next? Well, I see a y transformation here where I have to add 5 to all the y's, including that one. And I see one last x transformation where I'm supposed to divide all the x's by 4. So my points that I end up graphing will be 0, 5 and 2/3, 1/4, 7, and 1/2, 11. And don't forget a horizontal asymptote at y equals 5. So my graph, there's the horizontal asymptote, y equals 5, does this. It's an exponential growth curve. I know that because the base is bigger than 0, and there's a positive here. I'm sorry, the base is bigger than 1, and there's a positive here. So I'm going to label my points. This will be 0, 5 and 2/3. This will be 1/4, 7, and this will be 1/2, 11. Okay? Again, you're welcome to, draw that y-axis and put in an x-axis. But I find if you go much beyond that, your curve probably won't look like a smooth curve. You'll have made some points, and you'll be trying to do this through them, and it'll just be a tough time. Okay? So one last graphing one, please. Perhaps we're warmed up, and this should be comfortable. Log base 3 of x over 4 plus 1 minus 5. Okay, so now that you're warmed up, please graph this one. Okay, what reference points did you start with? Did you start with 1/3, negative 1, 1, 0, and 3, 1, with x equals 0, a vertical asymptote? I hope so. If you haven't memorized those yet, you really need to by the time you take that test. All right, I'm applying the y transformations, multiplying by 2, by 2, by 2. This is an x, so I don't multiply by 2. And subtracting 1 from all the x's, including this one. My transition points, negative 2/3, comma negative 2, 0, 0, 2, 2, and x equals -1 for our vertical asymptote. I'm going to come back now and subtract 5 from all the y's. And what is it that I have to do to the x's? I see dividing by 4, so that means I need to multiply by 4. All the x's, including that one. This gets so often ignored. Please, please remember that. So my final points are -8 thirds, -7, 0, -5, and 8, -3. Okay, and here we have x equals -4, the vertical asymptote. All right, so what does my graph look like? Well, it's a log graph with no negative in front, no negative in here. So I'm going to draw in that vertical asymptote at x equals -4, and then I'm going to sketch in my log curve and just label points. So I've got -8 thirds, -7. I've got 0, -5. That would be where the y-axis goes. And I've got 8, -3. The x-axis being up here somewhere. Okie doke. I mean, I find it so much easier to draw in the axes after I draw the graph. But if you're not really comfortable with, well, no, I don't want to say that. You really need to be comfortable with the shape of this graph. It's not that big a deal, and if you're not stepping up to it, you're kind of being lazy in this very college level class. So stop it. All right, how about these non-functions that you should be able to graph? How do we graph this one? You know, it does factor as y minus 1, y plus 1. And so we can find some y-intercepts by setting each of these equal to 0. I have a y-intercept of 1, a y-intercept of -1. What else can I say? Well, if I put in a y value of 0, then x equals -1. So this is my graph. You know, and again, it's you can, if you're willing to turn your head this way, then this is the y-squared graph shifted down 1. But down has to be this way, and the only way this is down is if you're looking in this direction instead of normally looking in this direction. So, you know, that could be a little challenging to do. But factoring and setting the factors equal to 0 will find my y-intercepts, and then I just need one more point, perhaps an x-intercept, by plugging in a 0 for y to help me out. All right, so now that we've done that one, why don't you do this one? Y squared minus 5y plus 6. Okay? Give it a try, and I look forward to seeing you in a moment and seeing what your graphs look like. Well, I won't get to see what your graphs look like, but you will, and you'll know whether or not you're ready for our test on this or not, or whether you should be asking more questions. I mean, really, I'm just going to say, you need to be watching all the videos. You need to be taking notes on all the videos on anything that you are at all not clear on all year long. You've got to do the homework. You've got to stay engaged and ask questions, and ask questions. Okay, so here it factors as y minus 3, y minus 2 equals x. And so I know that there are intercepts at 2 and at 3 on the y-axis. I see it's a positive y squared, so we're going to go this way. And if I wanted to find an x-intercept, remember I just plug in a 0 for y's. So this is 6, 0 over here. Now, where's this point? Well, I know that the vertex is always halfway between these intercepts. So, you know, the y value would be 2.5. 2.5 minus 3 is -0.5. 2.5 minus 2 is +0.5, and so I get -1/4 there. So -1/4 is the x, and the y value is 2.5. I would be fine with just these 3 points and the correct shape, You don't need to provide this, but I would be happy with these 3 points as well. But I do want to see 3 points on that graph, okay? All right, next and last, let's do some speed round stuff. Quick, and don't pause the video for this. Sine of 5 pi over 3. 5, 4, 3, 2, 1. You should have negative root 3 over 2. How about cosine negative pi over 6? 5, 4, 3, 2, 1. Root 3 over 2. Remember, negative pi over 6 is here. It looks just like 11 pi over 6, and we know that this y value is negative 1/2, but this x is root 3 over 2, and cosine is all about the x. How about tangent 5 pi over 4? 5, 4, 3, 2, 1. Well, our answer, remember, this is in third quadrant, and so we've got negative root 2 over 2 over negative root 2 over 2, and so yeah, we do get 1 there. Okay, what's next? How about cotangent pi over 4? 5, 4, 3, 2, 1. You should have 1 for that. Root 2 over 2 divided by root 2 over 2. Okay. How about cosecant negative 8 pi over 3? All right, I'll give you a few more seconds on that one. You may find it helpful to say negative 1 pi over 3, negative 2 pi over 3, negative 3 pi over 3, negative 4 pi over 3, negative 5 pi over 3, negative 6 pi over 3, negative 7 pi over 3, negative 8 pi over 3. Negative 8 pi over 3 looks just like 4 pi over 3. This will be the same as cosecant 4 pi over 3. And you'll know that to be the reciprocal of 1 over sine 4 pi over 3. What is the sine of 4 pi over 3? Well, the y value there is negative root 3 over 2. So I would expect negative 2 over root 3, or the rationalized version, negative 2 root 3 over 3. These are my answers to this one, okay? And how about 1 or 2 more? Tangent negative pi over 2. 5, 4, 3, 2, 1. That's right, this is where one of the vertical asymptotes are, so that's undefined. Remember, when we're graphing tangent, we set the argument, the stuff in parentheses, equal to pi over 2 and negative pi over 2 to find the vertical asymptotes. So that's a vertical asymptote for us. How about secant of 17 pi over 6? Secant of 17 pi over 6. 5, 4, 3, 2, 1. Okay, so I remember that this is too big. That's 12 pi over 6, plus 5 more pi over 6 brings me over here. So this looks like the secant of 5 pi over 6. I could get that by subtracting 2 pi from this to get it back onto the unit circle. Remember, we talked about coterminal angles in January and said, you know, if you've got this negative thing, you could add a period. If you've got this positive thing that's too big, you could subtract a period until you get something that's actually on the unit circle that you recognize. So this is 1 over cosine 5 pi over 6. We know the cosine of 5 pi over 6 is negative root 3 over 2, and so my answer to this is going to be negative 2 over root 3, or negative 2 root 3 over 3. Okay? So that's our review. It's just some of the stuff. I mean, exponential word problem, of course. You know, it's not to suggest that there aren't lots of other things. There are a number of reviews for this test. we have some worksheets to look at, and I'm actually going to make videos for those two worksheets, and there's bookwork to do. So you've got plenty of review. Um, I would watch the two review worksheet videos and do ask questions from those or from the bookwork before we have our test. All right. Take care, everyone. Let me know how I can help.